Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from Richard Feynman, who says that we have written an equation does not remove from the flow of fluids its charm or mystery or its surprise. It is a very indeed a great statement, because we always lose the sight of the physics while handling the equations. So, now we are trying to derive a lot of equation. We should keep this in mind. Let us recall now what we learned in the last lecture. We basically discuss about the various aspects of the first law of thermodynamics. Particularly, we have derived the first law of thermodynamics for a controlled volume system by considering the equation for control mass system, and then we looked at how it can be utilized for fluid flow and other rocket engines. And later on we also discussed about the second law of thermodynamics for a controlled mass system, and also subsequently we derived an expression for entropy balance in case of controlled volume system. Later on we moved into various aspects of the aerodynamics, and there we also jotted down what are the equations are required, like mass continuity, momentum conservation equation, and energy conservation equation, and equation of states. All these four governing equations are to be considered for analyzing aerodynamic problems, particularly for compressible flow. And of course, for incompressible flow we can only consider three equations, that is mass continuity and momentum conservation and energy conservation equations. Subsequently we derived both integral and the differential form of mass conservation equation. And today we will be discussing about the momentum conservation equation, and we can take the a arbitrary streamline with the control surface here, which is shown here in this place, and streamlines are moving through that, and we are considering an element, fluid element having a surface area of dA, which is moving at a velocity v, making an angle theta with its normal n. So, according to the second law of motion, we know that F is equal to k, the rate of change of momentum, and for SI unit the k will be 1. Therefore, force is nothing but your rate of change of momentum, and we will be applying this law of for deriving a momentum conservation equation for a controlled volume. And if you look at that is nothing but your rate of change of the momentum in this control volume, that is your rate of change of momentum is equal to the momentum flux. This is your momentum flux is equal to the summation of the force which is acting on the control volume. So, these forces can be of two kinds. One is surface forces and other will be acting on the volume. This is basically volume forces, and this stress will be the acting on the normal to the surface of this control volume, and that is basically the pressure which will be acting. This is your pressure. And shear which will be acting on the surface but along with the surface, whereas the normal force will be acting normal to the surface. And these forces which will be acting on the control volume, that will make the momentum to move across the control volume, and of course there will be accumulation of rate of change of momentum in the control volume, and that is known as the momentum conservation equation. And energy equation, as we have already seen, that is the rate of change of total energy, rate of change of total energy, which is consist of basically enthalpy and kinetic energy and potential energy, and this portion basically energy flux across the control volume is equal to the total heat interaction. This is, you can say that Q, and this is your shaft work, and the force and the work done due to these body forces. This is the work done by body forces, and this is the balance what you need to look at it. Keep in mind that this energy, as I told earlier, that E is nothing but your internal energy and this is your specific kinetic energy Ke, and this is your specific potential energy. Specific means basically potential energy per unit mass, and this is also specific internal energy. So, if you look at equation of state for an ideal gas is basically equal to P is equal to rho R T. Keep in mind that P is the pressure, rho is the density of gas, and R is the specific gas constant, which is equal to Ru, that is your universal gas constant, into molecular weight. This is your molecular weight, and Ru is the universal gas constant, and T is the temperature of gas. And keep in mind that we will be considering the ideal gas for most of the things, because we will be handling high temperature gases. Therefore, we can happily consider the gas to be an ideal or the perfect gas. And for an adiabatic steady one dimensional flow, that we will be considering now, because of fact that we will be using it very often. Let us derive it so that we will be familiar with it. So, let us consider a conversion nozzle which is shown here, and we want to in which the fluid is moving with a velocity of V1. Keep in mind this is the uniform velocities which is entering, and similarly it is leaving from the exit of this nozzle. This is your nozzle with the velocity, uniform velocity V2. That means all these things will be, velocity will be same across this. So, that is uniform. And let us consider this is my control volume and this is your station 1 and this is your station 2, and in this case there is no shaft work because there is no shaft which is there which is making some work. This is shaft work, and similarly we are considering there is no heat interaction because this is adiabatic walls. So, therefore, the q dot is equal to 0. So, considering this as a one dimensional also steady, that means there is no accumulation of mass, energy or momentum in this control volume. So, therefore, we can apply the first law of thermodynamics for continuity very easily. Of course, the mass conservation has to be looked at, and in this case the mass conservation will be that is m dot 1 is equal to m dot 2 and rho 1 v 1 a 1 is equal to rho 2 v 2 a 2. So, this is your mass conservation equation, and let us consider the first law of thermodynamics, and that is h 1 plus v 1 square divided by 2 is equal to rho 2 plus v 2 square by 2. Keep in mind that here we are not considering the potential energy term or the gravitational effect. So, therefore, what it says that total enthalpy at the station 1 is equal to the total enthalpy at station 2. I can write down this is amounts to be this expression. What is saying is basically ST1 is equal to ST2. Of course, I am going to define that later on, and you people are aware of that. So, that means if I use this one, H is nothing but your Cp and T. Cp is your specific heat at a constant pressure into T1 plus V1 square divided by 2 is equal to Cp2 T2 plus V2 square divided by 2. And we know that Cp for an ideal gas, Cp is equal to gamma r divided by gamma minus 1, and gamma we know is nothing but your Cp by Cv. Cp is the specificated constant pressure, Cv is the specificated constant volume, and R is your specific gas constant. R is nothing but your Ru by molecular weight. Ru is the universal gas constant that we have already discussed in the just a few minutes back, and that is turns out to be basically, if you look at CPT1, that is Cp21 is nothing but your gamma r gamma minus 1 into T1, and we know that equation of state says that by equation of state we know P1 is equal to rho 1 R T1. So, therefore, R T1 from here I can write down gamma R P1 by rho 1 divided by gamma minus 1. So, this is the term what we have basically this is nothing but your Cp T1, and then the next term as it is remained V1 square divided by 2 is equal to gamma divided by gamma minus 1 P2 divided by this will be rho 2 plus V2 square divided by 2. So, this is the expression for basically a compressible fluid, and for so far the energy conservation is concerned, right, and considering the flow to be one dimensional. So, if it is an isentropic flow, steady flow, then we can say that entropy is equal to 0, and when entropy is equal to 0, then we can invoke this equation T ds is equal to dH minus dP, and for isentropic flow this portion will be 0. That means what is saying that is dH is equal to VdP, and nu is your specific volume, that is 1 over density. So, you can now use this in the equation 5 and can get that this is and we can arrive at is equal to P1 plus rho 1 V1 square divided by 2 is equal to P2 rho 2 V2 square divided by 2. So, this you can easily get that, and maybe you can try it out. And so, this expression is very familiar. You might be aware that this is basically the Bernoulli's equation of which is valid for the incompressible fluid. Keep in mind P is the static pressure and rho V square is nothing but your dynamic pressure, and in this case gravitational effect is not being considered. So, then the equation 5 basically, as I told earlier, that becomes for an incompressible in the form of equation 5b. And for an ideal gas, equation 6 becomes is basically this equation 6 is Cp dt by T minus V dP by T is equal to we can, in place of Cp, we can place this expression, that is gamma r divided by gamma minus 1, which we have derived here, right. This is the expression, and minus r dP by P. Now, we know of course the P is equal to rho RT for an ideal gas. And then we can write down this rho, as I told, it is basically rho is nothing but your 1 by nu. So, the nu by T is nothing but your R by P, this in place of, and we know that gamma is equal to Cp by Cv, and we can basically put this thing as R by P is nothing but your nu by T, and having this thing. So, you can basically get from this expression P2 by P1 is nothing but your T2 by T1, provided you say that this is for an isentropic flow, therefore, this will be 0, therefore, this will be equal to 0. So, and this expression you know very well that this is nothing but your isentropic relationship between the pressure and temperature between two states. And using the ideal gas law, equation 7 can T2 by T1 you can write down from this ideal gas law, that is P2 by rho 2 and divided by basically for T1 you can write down P1 by rho 1, and from this you can find out basically separate out P2 by P1 to the together, you can put together P2 by P1 and then you can rho 1 rho 2 separately, and you can get an expression and that is equal to the P2 by P1 is equal to rho 1 by rho 2 power to the gamma. You can get this expression for pressure, density and temperature together, that is P2 by P1 is equal to rho 2 by rho 1 power to the gamma, is equal to T2 by T1 power to the gamma divided by gamma minus 1. So, if you look at this, basically the energy equation for this one dimensional steady flow is same as that of the momentum equation. We have seen that we have derived this equation 5b, which is the Bernoulli's equation, from the equation 5, which is the energy equation. So, that means the momentum equation and the energy equations are same, particularly for one dimensional steady flow. That you keep in mind. A question might be coming into your mind that why we are using the isentropic, although in nature it is not so, quite restrictive in nature, but keep in mind that, as I had discussed earlier, that most of the flow, except in the nearby of the boundary layer or within the boundary layer, flow we can consider as to be isentropic in nature. In other words, viscous effect will be there or dissipative effect will be there. However, outside the boundary layer, the flow will be basically isentropic flow, or we can consider it as an inviscid flow. So, in case of high speed flow or the compressible fluid, the boundary layer thickness is very small, because and then we can consider as to be, and beside this, for a nozzle, for a other things, length won't be that great to the boundary layer to grow. Then we can consider the flow to be isentropic one. But however, this is an ad hoc solution or ad hoc way of analyzing it. The best way is that we can consider the isentropic case also. Keep in mind that due to the inadequacy also within a short time or with quickly we want to get the solution, therefore, we are using it. And let us look at something about the speed of sound, because that is basically important for defining the compressible fluid, and we will be looking at that, because whenever there is a disturbance, it will be moving with certain velocity corresponding to the speed of sound. Therefore, we will be relating to the velocity of the fluid, and the speed of sound is basically, if you look at, is a compress, which says about compress. That means there will be change in pressure. This is your P, pressure, and with respect to change in density, because if the compressible fluid, there will be change in density, and considering it is to be isentropic flow, the speed of sound is basically defined as the change in the pressure with respect to density change for an isentropic flow. Root over of that we call as the speed of sound. And using the ideal gas law, we can derive it. You please derive it yourself, and which turns out to be root over gamma RT. Gamma is your specific heat ratio. This is your specific heat capacity ratio or specific ratio. R is the universal gas constant, as I told earlier. T is the temperature. So, what it indicates, the speed of sound is dependent on the temperature for an ideal gas, and it will be dependent on also the specific heat ratio. And if you look at you consider the two fluids, that means it depends on also the kind of fluids through which the sound wave is moving. And if it is air and the temperature of this air happens to be 300 Kelvin, the speed of sound is 340 meter per second. However, when the temperature increases to 1000 Kelvin, the speed of sound is 634 meter per second. But if you use 300 Kelvin and instead of air you are using helium, or the sound is propagating through the helium, then the speed is much higher, that is 1019 meter per second. And so also temperature is increasing in the 1000 Kelvin, that is 0.61 meter per second for helium. So, the speed of sound, what we have seen, is a function of temperature and also the type of fluid through which it is moving. The Mach number which we will be using for our case, and that is being defined as the ratio of velocity and the speed of sound, and which is nothing but a v divided by root over gamma RT, because this is the expression for the speed of sound. And Mach number is very important because that will dictate the flow regime. If the flow Mach number is less than 0.08, we call it a subsonic fluid, and the Mach number is between the 0.8 to 1.2 is known as transonic fluid, and Mach number is equal to 1, that is the velocity of the flow will be equal to the speed of sound, we call it as a sonic flow. And when Mach number of the flow is between 1.2 and 5, we call it supersonic flow. When the Mach number of the flow is greater than 5, we call it as a hypersonic flow. So, we will be dealing some of these fluids, both the subsonic and supersonic flow, which will be occurring in a rocket nozzle. Therefore, you should keep this in mind. And I have just shown you little graphically that this is about basically when the velocity is low is an incompressible fluid, and when it is higher the velocity of the fluid is subsonic, and this is your transonic fluid, and of course, the supersonic fluid between the 1.2 of Mach number to 5, hypersonic greater than 5. So, let us understand what do you mean by stagnation point. When the velocity of the fluid is brought to 0 or having a standstill isentropically, then we call it as a stagnation point or the isentropic conditions, right, stagnation point. Then the energy equation becomes is equal to ST, as I told, total enthalpy. For a one dimensional flow, the total enthalpy remains constant, particularly for adiabatic and also when there is no work done going on. So, there is again we can write down Tt is equal to T plus V square by 2 Cp. Let us take an example where air is velocity moving at 100 meter per second, and then at this point when it is uniform, it is in the wedge, it is brought to this fluid into, if you look at this fluid is coming and bringing to the standstill, and then of course the fluid may move to that, right, this may go over here, right. So, then there will be this velocity which will had very higher, and it will be converted into certain velocity head, that is converted temperature. Therefore, at this point, this is the kernel point where the temperature will be higher, which is experienced by the wedge, this point, cone point, and total temperature will be consist of the static temperature. This is your static temperature, and this is your dynamic temperature. So, as I told that this already I have explained, Tt represents the temperature that an ideal gas attains when it is brought to rest isentropically. Total property ratio which we will be dealing with, because equation 10 we can convert into Tt, I can divide this equation 10 by temperature here and so also temperature here, and we can get in terms of that is gamma minus 1 divided by, because Cp is nothing but your Cp is equal to gamma r divided by gamma minus 1. So, V square by 2 you can keep, this is basically is nothing but your A square, and this V by A is nothing but your Mach number, and so therefore, Tt by T is equal to 1 plus gamma minus 1 divided by 2 Mach number square. This is an expression for the temperature ratio, particularly total temperature and static temperature ratio. Similarly, we can derive the expression for total pressure and pressure in terms of Mach number for an ideal gas, that is Pt by P is equal to 1 plus gamma minus 1 divided by 2 m square, power to the gamma divided by gamma minus 1. So, you can look at different altitudes. You can see that is given here, the temperature 288 Kelvin in the 10 kilometer altitude, it is 223, and V is 100 meter per second. You can say the 500, the speed of sound is changing, so also the Mach number will be different. And keep in mind the total temperature, which will be also one can calculate, because the dynamic head, depending on that it will be. So, you can find out this is the total temperature you can evaluate from using this formula, and which will be using this in our calculation. And thank you very much. In the next class, which about basically certain combustion aspects, so that we can look at how to handle this reacting flow as well. Thank you very much.